Okay, today we're going to do proof by contraposition. This is section 5.1 in the textbook. The textbook calls it proof by contrapositive. To my ears, I don't think that is as correct of a way of saying as proof by contraposition. You see, we're going to use the contrapositive of a statement to prove the statement. So it's a proof using the contrapositive, but what we're doing is an action, and that's why I think it's more correct to use the wording proof by contraposition, because the action that we're doing is we are doing the action of contraposition. Okay, and what it is this. You know that most theorems are conditional statements, right? So you have P implies Q. Most theorems are of that form. And you also know that the contrapositive of that is not Q implies not P, or maybe we should say the negation of Q implies the negation of P. And the third thing that you should know is that a conditional statement and its contrapositive are logically equivalent. Therefore, if we prove this, we will be backhandedly proving this. Okay? If you want to prove this directly, what would you do? You would assume P and deduce Q. If you want to prove this one directly, you would assume the negation of Q and deduce the negation of P. But that direct proof of this would also be proving this, since they're logically equivalent. So, the bottom line is, if you want to prove this, and you do so by proving this, then what you're doing is you're proving this by contraposition. Okay? All right, so that's all there is to it. Now it's just a matter of practicing it. So let's do this example here. Okay, it says, suppose x is an integer. Okay, then the claim is if 7x plus 9 is even, then x is odd. Okay, so here's P and here's Q. Okay, given that x is an integer. Okay, so let's prove this first directly, just to show that it can be done directly. Okay, where we will assume P and deduce Q. Okay, let me write that down. So we're going to do proof. This will be direct. All right, we're going to assume P and deduce Q. Oh, that's an ugly Q. Let me fix that. Looks almost exactly the same. Okay, so let's do that. All right. So what I'm going to do is I'm going to write, let x be an integer. And suppose 7x plus 9 is even. Okay. Then what? What does that mean? Well, we know what the word even means. If 7x plus 9 is even, then 7x plus 9 equals 2 times an integer, right? 2 times, what do you want to call the integer? Well, the book calls it a, so I'll go ahead and do that. 2 times a. Okay, but not just it equals 2 times a, it equals 2 times a, and also a is an integer. That's important. That would be meaningless without pointing out that a is an integer. Just because something equals 2 times something does not mean you have an even number, unless that something is an integer. Okay? All right, now I want to show that x is odd. In other words, why don't we solve for x? And before we do that, let me even say here, it's not a bad idea. I should say, why did I get that second line? It was by definition of even. There we go. Okay. All right. Hence, what would x have to equal? Isn't it true that x would equal 2a minus 6x minus 9? I guess I didn't really solve for x, did I? Because I still have an x over here. So I misspoke slightly when I said solve for x. What I should have said is I want to move everything to the right except one of the x's. That's how I should have said it. Okay? All right. What am I trying to show? I'm trying to show that I'm trying to show that x is odd. Okay? Is this an odd number right here? Well, what does it mean to be odd? Odd means an even number plus 1, right? So is that thing circled in red an even number plus 1? Sure, it is. Because it equals 2 times what? A minus 3x minus 5 plus 1, right? Do you agree with that? And what else is important? This number is what kind of number here? I've said that x is an integer. I've said a is an integer. So a minus 3x minus 5 is an integer, right? Where a minus 3x minus 5 is an integer. Therefore, X is odd by the definition of odd. Well, we oftentimes don't put the word the. We oftentimes just say by definition of odd. Okay, that was an easy proof, wasn't it? Just 4 lines, and it would just require some basic algebra and knowing the definition of even and the definition of odd. Okay, now, just for comparison purpose and practice, we are going to prove it again by contraposition. So this time we are going to assume the negation of Q and deduce the negation of P. Okay, so this time we'll say let X be an integer and assume or suppose that X is not odd. Okay, then what is X? X would have to be even. So I could write X as what? X would equal 2 times an integer. So that means 7x plus 9 would equal, wouldn't that be 14a plus 9? And what kind of number is 14a plus 9? Wouldn't that have to be odd? Because that is 2 times 7a plus 4 plus 1, right? And 7a plus 4 is an integer. Which means that 7x plus 9 is what kind of number? Odd. Okay. Now, if it's odd, then it's not what? It's not even. Do you need to say that? If you said it's odd, do you have to say it's not even? I don't think it's required. I think I think odd means the same thing as not even. It has a different definition, okay, but we all know that every integer is either odd or even. I believe that's even been proven in our book already. So if you say something is odd, I don't think it's mandatory to say it's not even. I believe that odd is already known to be equivalent to not even. At the same time, there's absolutely nothing wrong with just being extra careful and covering your bases. Okay? Now, if you're reading in the book on page 129, that's the end of their proof. Now, I think, this is my opinion, when you're doing a proof by contraposition, it is definitely not a bad idea to point out at the end what you've done. Here's the reason why. Let's look back at the proposition that we're proving, okay? Let's go ahead and shrink this first proof out of our way. And let's move this up. Okay, so let's pretend that you're the person who's reading this, and you see this. Okay, what is it that you notice? You notice that the proposition is saying that under certain conditions, x will come out to be odd. So it's reasonable to think that the reader is going to be expecting the end of the proof to say, therefore, x is odd. And they're reading through the proof, and what do they find at the end? Something totally different than x is odd. Okay, now an astute person should have been able to follow what's going on here and to notice, oh, they're doing proof by contraposition. But nonetheless, sometimes those things go a little bit past somebody without them noticing. And all I'm trying to say is somebody might be a little confused because they might be thinking, you're trying to prove x is odd. Well, what's their mistake there? We're not trying to prove x is odd. We're trying to prove if 7x plus 9 is even, then x is odd. That's what we're trying to prove. We're not just trying to prove x is odd, right? But nonetheless, it's very common for people to see this proposition and to be expecting that this is what we are working towards at the end of the proof. And then they get to the end of the proof, they see this, and they think, wait a second, I thought we were going one direction and whatnot. Okay, so I'm just saying that we did this proof through the back door, if you would say it that way. And so, it's reasonable to think that somebody might say, oh, wait a second, how did you get into this room? And you might have to say, oh, I came in through the back door, that's why you didn't see me. Okay, so it's not a bad idea, in my opinion, if you're doing proof by contraposition, to wrap up the proof by saying, that if the hypothesis, then, whoops, I didn't finish writing the hypothesis. I forgot the words is even. Then, and our conclusion. And even to say, by contraposition. Okay? Do you have to do that at the end? No, but I think it's a really good idea. In fact, I think putting that line on is even more important than pointing out a number that's odd is, by the way, not even. Okay? If you're saying, if you get to this point right here, and you say, I will write one more line, I refuse to write any more than that, then I would say, okay, then we could definitely do without that one. But let's keep this. Okay? So that's a proof by contraposition. Is that any easier than the direct proof? No. It's even a tiny bit longer. The direct proof was 4 lines. This one is 6, as it is written right now. Okay. But it is a tiny bit easier just in this sense right here. In the direct proof, which has now been deleted, Remember, we had 7x plus 9 equaled 2a. And I subtracted 6x plus 9 from both sides. And ended up with x equals 2a minus 6x minus 9. At that point, you might have asked yourself, how would I have thought to subtract 6x plus 9 from both sides? And I would say, well, if you do this proof by contraposition, then you don't even have to worry about thinking of that. Here in the proof by contraposition, you just have x is even, and that gets us here, and then we just plug 2a into that, and you get this. It's very, very reasonable and straightforward. Okay? Now, in the next example, I'm going to show you one where a direct proof would be doable, but quite a bit harder than a proof by contraposition. Okay, let's look at this one. Suppose x is an integer. If x squared minus 6x plus 5 is even, then x is odd. Let's prove that. And let's try doing a direct proof. So we'd say let x be an integer, and suppose x squared minus 6x plus 5 is even. Then x squared minus 6x plus 5 equals 2a for some integer a by definition of even, hence x would equal, okay, now it's not quite as obvious of where I would go from here, is it? I mean, I could think of some possibilities. I could say x would equal 2a minus x squared plus 7x minus 5, right? Look at that for a second and make sure that you agree that the algebra I did there is not false. Okay, you got that? But here's the problem, though. What would I now do with that information? Trying to show that that's odd. How would I do that? Because if I did it like I tried in the previous example, if I wrote, oh, well, let's see, that would be 2 times something plus 1, right? What would be the something that would go right here? Well, let's see. It would have to be a minus, and here's the problem I'm going to run into, 1/2 x squared. And here's the same problem that's going to happen here, plus 7/2 x minus 6. The problem is those two fractions. How do I know that this thing is an integer? It's not so clear this time, is it? So, I'm confident that we could figure it out, but I really think that a proof by contraposition will be much easier here. Okay? So, let's abandon this tact and try proof by contraposition instead. So we'll say let x be an integer, and suppose what? What should we be supposing here? We should say suppose x is not odd. Like I said earlier, I don't think that it is necessary to say here x is not odd and then in the next line say therefore x is even. If we want to suppose x is not odd, then to be honest with you, I'm going to say then x is even. Okay? We are supposing the negation of this. And the negation of being odd is being even. Okay? That's how I would do that. All right? Then x equals 2a for some integer a by definition of even. Hence, see, now it's totally obvious where to go from here. Okay, I assumed the negation of this. I want to deduce the negation of this. So in other words, I'm trying to show that this is an odd number. If this is even, then this is odd. Okay, so where do you think I'm going to go from here? Well, I have x equals 2a, so I'm just going to plug that in here. I think it's very clear where to go. So what would x squared minus 6x plus 5 equal? It would equal 4a squared minus 12a plus 5. I'm trying to deduce that this is what type of number? I'm trying to deduce that this would be odd. So let's write it in a way that fits the definition of odd. 2 times an integer plus 1. So I will write that as 2 times 2a squared minus 6a plus 2 plus 1. Why is this so much better than when I started doing a direct proof? Because here I have no fractions. So it is clear that I have 2 times an integer there. And then the plus 1 makes it odd. Okay? So let's finish this sentence. Where 2a squared minus 6a plus 2 is an integer. Okay? Thus, x squared minus 6x plus 5 is odd by definition of odd. Therefore, oh, why don't I go ahead and show you, by the way, there's a symbol for therefore. I didn't want to do it right away, but now I think it's fine to show you this. Most of you have seen it anyways. Those 3 dots in that particular pattern is a symbol for therefore. Okay, so therefore, if x squared minus 6x plus 5 is even, then x is odd by contraposition. Okay? So it's pretty straightforward. In this case, the proof by contraposition was way easier than a direct proof would have been. Okay, let's try this one. Suppose x and y are real numbers. If y cubed plus xy squared is less than or equal to x cubed. I'm sorry, I believe I misread that. Let me start this one over. Suppose x and y are real numbers. If y cubed plus yx squared is less than or equal to x cubed plus xy squared, then y is less than or equal to x. Okay? Let's prove that by contraposition. I'm not even going to start doing this directly, not because you shouldn't or anything, but just because I want to practice proof by contraposition. Okay, so we're going to do it that way. So let x and y be real numbers, and suppose, what should I be supposing here? I should suppose the negation of that. What's the negation of y is less than or equal to x? The negation is x is greater than y. Or if you prefer, oh, sorry, I said greater, and I meant the other way around. It should be x is less than y. Or if you prefer, y is greater than x. It doesn't matter which one. You want to write it like this, that's fine. You want to write it like this, that's fine, either way. Okay, I'll just write it as y greater than x. That's the negation of y is less than or equal to x. Okay, now what does it mean to say y is greater than x? I believe that has been defined. Has it not? What it means for one number to be greater than another means that the supposedly larger number minus the supposedly smaller number is positive. That's what the word greater than means. Okay? So y minus x would be positive. That's the definition of greater than. Okay. Now, where are we going to go from here? Let's think about this, because it's not as obvious as the last one. We're trying to get down to what? So we assumed the negation of this. We're trying to deduce the negation of that. So we would like to get down to y cubed plus yx squared being greater than x cubed plus xy squared. How are we going to get there from here? Well, it's not obvious, is it? How to get from here to here. But what about this? What about if we say, well, what line would come right before this one? Maybe that would make it a little bit easier. So, okay, if this is greater than this, where would that be coming from? Well, again, definition of greater than, that would mean that we would have to have had y cubed plus yx squared minus x cubed minus xy squared would have to be greater than 0, right? So instead of asking yourself, how do we get from here to here, let's ask ourselves the question, how do we get from here to here? Maybe that's easier. And I actually think it is easier. Do you recognize this part? Having a relationship to this? maybe let's take those two terms and switch the order. Instead of negative x cubed minus xy squared, what if we were to write negative xy squared minus x cubed? Now do you see a relationship between that and that? There is one. I'll tell you what it is. This is equal to that times x squared plus y squared. And what can I say for certain about x squared plus y squared? No matter what real numbers x and y are, I know that x squared plus y squared would be what? Non-negative. So if I multiply this by a non-negative number, I will get that. And if I started out with something positive and multiply by a non-negative number, I'll still have something positive, won't I? Okay? That's the plan I'm trying to formulate. Let's follow that plan through. So let's go where we left off. Y minus x is greater than 0. Okay, hence y minus x times x squared plus y squared would be greater than 0, since x squared plus y squared is non-negative, which means does not turn that inequality around. What I did was I took this and multiplied both sides by x squared plus y squared. The right side didn't change because 0 times x squared plus y squared is still 0. The important part is that because x squared plus y squared is not negative, then this inequality did not flip. Okay? Now, I'm going to simplify this. Okay? And that is, whoops, wrong color. That is y cubed plus yx squared minus xy squared minus x cubed. Okay, that actually I realized I want to bump this over and make some room here. How I prefer to say it is to say, but the thing I have already equals this. Okay, so this thing is greater than 0 because I am substituting it in right here. Okay? Thus, y cubed plus xy squared is greater than x cubed. Sorry, I again said xy squared when I should have said yx squared, is greater than x cubed plus xy squared. by definition of greater than. Okay, therefore, by contraposition, if y cubed plus yx squared were less than or equal to x cubed plus xy squared, then y would have been less than or equal to x. Okay, you see how that is? Now, I could have made this one line shorter by combining these two. And this is how it would have looked. I would have had the second line, then y minus x is greater than 0, and then hence I could have said y cubed plus yx squared minus xy squared minus x cubed equals y minus x times x squared plus y squared, which is greater than 0. Okay, that one line could have been a combination of those two. Why didn't I do it that way? Because I like to give some thought to when somebody's reading this, I want them to not have any questions. Okay? When someone's reading your proof and they're lost at one step, then the first inclination is I wasn't clear enough. Not always, because maybe the thing that they're lost on is something trivial that they should definitely not be getting lost on. But for the most part, when someone gets lost on a step in your proof, your first thought is I wasn't clear enough. And I think going straight from here to here is a somewhat large step. Okay? It's not undoable. I mean, I'm not saying, oh, you would never do that. I'm just saying I feel that that might be a place where somebody would get lost on when they start seeing this, because we read from left to right, correct? So that's the first part they would see. And I'm worried that they would think, well, I have no idea where that came from. They might not even get this far, because as soon as they get here, they might think, oh, I need to figure out where that came from before I go even further, any further. You see what I'm saying? So I tried to make it more obvious to the reader. I had that, and they should definitely understand where that came from. And then I show them, okay, now I'm going to multiply both sides by x squared plus y squared. And by the way, the left-hand side can be simplified into this. Now I feel like, okay, I was very clear. If they get lost now, I feel like, okay, then the problem is more on them than it is on me. You have to take those things into account when you're writing proofs. It is not a 100% science. There is some art to it. And you have to take things like that into account. Okay? Something else, and this is just totally minor. It doesn't even need to be brought up, but I think I'll bring it up anyways. My personal feeling is that a well-written, elegant proof, every line will start with a word. Now, I'm willing to bend that rule right here. I'm fine with the last word starting with the 3 dots that stand for therefore. Okay, I don't have a problem with that. I think it's nice to actually write out the word therefore, but it's kind of a long word, and I'm fine with those dots. Now, technically, the first word of that sentence is therefore, correct? However, visually, it looks like the first word is by. It's not. By is actually the second word, but when you look at it, it looks like the first word is by. And we all know that the first word of a sentence should be capitalized. So some people would do this. And grammatically, the B should not be capitalized because by is the second word and not the first word. But visually, it does kind of look better this way, because visually it looks like by is the first word. So I'm just, that's just very trivial, and it doesn't even need to be brought up, but I'm just saying it's an interesting discussion. I think it looks nicer with the B capitalized. That's an example of a situation where even though I think your proofs should be grammatically correct, and if they're not, you should expect to get some points off, okay? But this is an example where I'm okay. Grammatically, the B should not be capitalized, but I'm okay with the B being capitalized. I don't know. That's neither here nor there, but I just think it's an interesting discussion. All right, let's do one more. Okay, last example. Suppose x and y are integers. If 5 does not divide xy, then 5 does not divide x, and 5 does not divide y. Now here's one where you would definitely want to go by contraposition, because if you started out this way, one second. If you started out, let x and y be integers, and suppose five does not divide xy. Here's the problem that we run into there. This leaves open infinitely many possibilities. Remember, to say A divides B means B equals A times an integer. That's a very specific, narrowly defined thing. To say A does not divide B means that B does not equal A times K for any integer K. That's a much wider defined thing, isn't it? So, we will be better off this time not starting with something so vague as 5 does not define xy. So we're going to do proof by contraposition instead of a direct proof. And so what should I be supposing? Now be careful here. It is not this. It is not that. Because, why? I should be supposing the negation of this. Now remember, the negation of P and Q is what? It's the negation of P or the negation of Q. Whose law is that? That's De Morgan's law. Okay? So what I should have here is 5 divides x or 5 divides y. Now again, that should be clear, but reasonably I can see somebody maybe getting stuck and saying, oh, wait a second, why do we have this here? Why is that an or and not an and? So I think here's a situation where I think it is worth my time, so that I don't have to explain that to anybody. It's worth my time to point out what it is I'm doing. So I think I would say this. Suppose it is not the case that 5 does not divide x and 5 does not divide y, and I had better put parentheses around that. Or if you don't think that's an appropriate place for parentheses, you could do quotations. You just want to make it very clear that you're not saying the negation of this one and this one. So I don't want people to think that I'm saying x 5 does divide x and 5 does not divide y. I want to make sure that they don't think that the negation that I said right there, it is not the case that. I want everybody to be clear that that negation is applying to this whole thing, not the negation is applying to just this. And then I have the conjunction with that. Okay, I don't want any confusion. Okay, so suppose it is not the case that 5 doesn't divide x and 5 doesn't divide y. Okay, then 5 does divide x or 5 does divide y by De Morgan's law. Okay. So I have how many possibilities here? I have 2. Maybe 5 divides x. Maybe 5 divides y. So what do I have here? I have proof by cases. Okay, we would do, the first case would be, now let's talk about this for a minute. First case would be suppose 5 divides x, and then we would go from there. Okay, and hopefully, what by the way am I hoping to get to? I would be hoping to get to 5 would be dividing xy. Okay, and that would be my case 1, right? And then my case 2 would be, on the other hand, suppose 5 divides y, and I would hope to get to 5 divides xy. That would be my case 2. And then I would have, therefore, in either case, 5 would be dividing xy, right? Now, that's actually the way it's done in the book, but let me ask you a question. Is there any difference between this case and this case other than a naming? I think no. I think those two cases are mathematically identical, only difference being, do I name the number that's being divided by 5 x, or do I name it y? And what did I say that you can use when you have multiple cases, but those cases are mathematically identical? You can use this trick without loss of generality, right? You can only use that when the cases are mathematically identical, not kind of the same, not the same basic idea, not, well, if you could figure out the first case, then you should be able to figure out the second case. But when the two cases are mathematically identical, the only difference being the name of something involved. In that case, you can use without loss of generality and only do one of the two cases. Okay, so that's what we're going to do. So this is where we're leaving off. And then I'm going to say, without loss of generality, which most people abbreviate because it's such a long phrase. Suppose, and then you do one or the other, either 5 dividing x or 5 dividing y. Let's just say suppose 5 divides x. Okay, what does that mean? Then x equals 5 times an integer. Because that's the definition of divides. So what would x times y equal? Would not x times y equal 5k times y? And wouldn't that equal 5 times ky? And wouldn't ky be an integer? So doesn't that mean that 5 divides xy? Okay. So now I think I would round it off, tie everything up in a nice little bow by saying, I believe that I would say, thus, in either case, five would divide xy. Okay, therefore, by contraposition, if 5 does not divide xy, then 5 would not divide x, and it would not divide y. There we go. That one's a really good example. I like that one. It practices contraposition, it practices proof by cases, it practices using without loss of generality. So that's a very, very good example to end on.